Thank you everyone for being with us this afternoon. My name is Yi. I'm the director of XR at OPPO. OPPO is a leading manufacturer of smartphones based in Guangdong, China. And as the chair mentioned, we have been working in AR for quite a while. We've been developing prototypes of AR 3 years ago, and we also developed a dev kit, which is a split design where we use a cell phone to power the AR glasses. And last year we did a monocle, green color only micro LED monocle, which we are selling now in small quantities in China. And we are actually showcasing these devices at booth 225, so you are welcome to check them out. But today I'm going to talk about something different. I'm talking about something more fundamental. How can we create content? So to begin with that, I want to talk a little bit about the value of digital twins for XR, why we think they are important. So if we look back at the evolution of personal computing, at the beginning we had PC, we had mouse and keyboard. These are almost, we can think of them of as a 1D interactions. And then we had some applications, for example, e-commerce, web portal, news sites, nothing fancy. Then the evolution went on, and then we were in the smartphone era. We have the smartphones, touch screens, and we have 2D multi-touch interactions. And this shift in paradigm, interaction paradigm, brings us the new applications such as shopping, social media, navigation, everybody is using nowadays. And what's next, right? So as a phone company, we really think the natural way to go is to go a higher dimension from the interaction, right? From 2D interaction to 3D. And these are 3D really natural interactions, including voice, gesture, and even brain-computer interface. And we believe XR device is a perfect fit for these 3D interactions. And we believe this will bring in a 3D internet ecosystem with all kinds of 3D applications like 3D movies, 3D shopping, 3D games, so on and so forth. To achieve that, right, we really need 3D contents. And we need 3D contents that are digital copies of the real world. Imagine if you are doing a shopping, you want to purchase furniture, you want that real world, your room to match the virtual furniture, right? So that you need a digital copy of the furniture itself and also your room. And also, since we are a phone company, we already have these cell phones in the hands of the users, right? So one question we asked ourselves is that, can we do this content creation from a mobile device using just one camera, right? That's the simplest setting. So this was the question, and I'm going to talk a little bit about what we have been doing. So one fundamental building block in all these technologies is that with the advancement of AI, or deep learning, we can now estimate the depth map from a monocular image, right? So on the left, this is the input image, and the goal is we can just from this, looking at this image, we can estimate the depth, right? So this is the depth map. The color code means different things, right? So the yellow color means the pixel is closer to the user, and then this purple magenta color means it's farther away. And this is the building block of everything we do here. And before the deep learning era, this was not impossible. We need kind of 3D imaging, ToF sensor, LiDAR, everything. Also, we might heavily rely on some traditional computer vision algorithms. But with the deep learning, data-driven approach, that's now possible. And the key idea, this might be a little bit too much detail, but the idea is that we can have some machine learning model to look at the image and estimate a depth map. We can also have a machine learning model to estimate the pose, sort of doing a SLAM using machine learning. Then, based on this estimated depth map and the pose, we can try to resynthesize the image and then compare this resynthesized image with the grand truth. And this error we can back propagate through the network to optimize the network, make sure that the network can predict a good depth map. But there's one problem with this existing approach is that for indoor environments, it tends to give a low quality depth results. So that's why we want to improve on that. We made some observations, right? So in AR or XR settings, we are typically confined in our rooms doing experiencing these games, videos, media. And in rooms, there's one problem is that the depth range are very inconsistent. Sometimes you only get 1 meter at your farthest, but sometimes in a living room or conference room, you might go to 10 meters, right? So that actually created problems for the existing methods. Another limitation is that for AR, right, we are in a room, we are looking around on our phone or using our device. What we are typically doing is a rotational dominant motion, but these algorithms, they cannot really capture the rotation accurately. So what we did is we proposed a new method called MonoIndoor, and it takes care of these two limitations. So one key component is something we call a depth factorization module. So what it does is in two different branches. One branch, it's called a depth network. It can still, from the image, run through a deep networks and get a depth map as the color visualization over there. And also, there's another branch. This branch, we call it a scale network. We take the features from the depth encoder, and we also use non-local blocks to learn the scale information. This scale information really means that that indicates the maximum depth range. For example, in a conference room, the scale network may produce us, say, 10 meters or 20 meters, versus in a bathroom, it's 2 or 3 meters. And then by multiplying the depth factor with the depth map, we can get a much better estimation. So another component or improvement is called residual post estimation. So the idea is really simple, right? So we believe we cannot do it once in one shot. Then we do it multiple times so that we can estimate the post in an iterative fashion. So with this improvement, this is kind of quantitative evaluation results. The bold color is our final results. We believe we can achieve the best results compared to the state of the art. And these are the color visualization. If we look at the last column, hours, you can see our depth map is much smoother and also it has a clear boundary around the depth discontinuity. And these are more results. So some key takeaways from this MonoIndoor method is that we believe self-supervised depth estimation can already achieve really good performance. So this is something I didn't talk earlier. So what we did here is a self-supervised learning. That means we don't require any ground truth data, right, compared to supervised counterpart. So for a supervised deep learning method, they need to use some 3D imaging sensors to collect a bunch of ground truth depth data. We don't need that. We can do this in a self-supervised manner. However, the accuracy is far from perfect, and also the temporal depth consistency is not good enough. So you can see those flickering when we play back the video. And they cannot be directly used for global dense mapping. Global dense mapping really means you want to create a global consistent mesh for your room or for your living room, bathroom, so on and so forth. So this leads us to a second innovation, what we call a GeoRefine. So it is a system composed of 3 different modules, but the key idea we want to get is how can we, a key question, right, we want to answer is how can we get accurate depth mapping? So there are several things we did here. The first one is that we combine this with a geometric sline, traditional geometric sline algorithm. We take what's good from there and combine that with an AI-based one. Also, we came up with a new algorithm called online self-supervised refinement. We try to use the SLAM data to optimize the depth prediction model. Finally, we use something called a TSDF fusion to create these global 3D reconstructions. So this is a pipeline. So on the left, this is a new SLAM system based on Raft flow. Raft is a new optical flow algorithm. And then this SLAM module produces the camera poses and also those sparse map points. If you understand what SLAM is about, the 2 most important information they can get is pose and the sparse map points. And then these pose and the map points gets fed into our online depth refinement module. So the idea is that we train a depth model, right? We train a deep neural network model to predict depths, but it does not generalize well for all kinds of different unseen scenarios, right? So we use the real data from your particular room to improve again your model so that your model can perform better for this particular thing. So that's what this online depth refinement is about. And then the depth maps and also the camera pose spots map points are fed into a global mapping system. So here is some kind of results. By the way, these are still in early stage research mode, but we are planning to make these becoming part of our XR toolchain so that developers can use them easily in the future to develop enticing XR experience. So on the bottom left, this is the input feed. Remember, we are using only one monocular image. And on the right, this is a 3D model we are creating on the fly. Yeah, let's. So some missing pieces, or I think there are still something we can make this system better, right? So first one is that, remember, we are only using one single image as input. So what if we can look at the video, right? Take the video as input. Can we improve further all these algorithms and the systems? And the second one is no semantic information. I believe semantic information is really important for AR, right? For example, if we want to do an AR shopping app, if I go to a website, I pick a lamp, I want my algorithm or my AR system can place that virtual lamp on my tabletop instead of on the ground, right? So that requires the semantic of information. We want to know if this picture or if this 3D space belongs to a tabletop or a ground. So that's also very important for AR specifically. So these are the questions where I asked just now. Can we leverage multi-view images? Can we leverage the structure information? There are a lot of planar structures in the room, tabletop, walls, ground. Can we leverage them? And also, can we predict the semantic labels? So this leads us to our final innovation. Is something we call a PlaneMVS. It's a paper we are going to publish in CVPR later this month in New Orleans. So the traditional, there are two different streams of work. The first one is single view plane reconstruction. So they take one image, they can detect the plane, they also regress the plane geometry, and then they combine them together. And this is one popular stream of work. The other stream of work is that these algorithms, they call the MVS, multi-view stereo. They can take multiple images as input, and then they can try to estimate the depth map from these multiple images. So our idea is that, our proposal is to combine these two, right? So we can take some good stuff from the plane reconstruction network, basically means the plane detection branch. We can also do a PlaneMVS branch, which means we use the MVS model, enhance that with the plane information. So the basic idea is that we looked at a bunch of data, right? All these indoor environments, and then we figured out the statistics of how these planes will look. And these statistics, we sample from this space a uniform distribution from this space, and then we use these plane parameters to process our images, and these processed images are passed through a neural network to estimate the per pixel plane parameter and also the depth map, right? I'm skipping a lot of details, but if you are interested, you can find our paper online. So this is a results here. On the left, this is the input video sequence. On the right, this is, again, the color-coded depth map. But in the middle, this is something interesting, right? This is a color-coded plane reconstruction. For example, the green means we find a wall, and the yellow means we find table, right? So why this is important, right? Imagine if you, again, going back to the furniture shopping example, if you want to buy a sofa, you want that experience to happen on your ground plane instead of on your tabletop. So with that, I'm concluding my talk today. So I talked about how to build digital twins, right, from monocular images. There are a few elements I talked about. The first one is we believe self-supervised learning is the way to go. We don't need to have a lot of ground truth 3D scanning data to supervise or to train our model. And we believe online depth refinement is something important because when we take our model to a new room, to a new configuration, we want to use that data to improve our model. And we also believe the traditional non-deep learning geometric SLAM system still has their merit, and we want to combine our method with these traditional geometric SLAM. And then we want to utilize the multi-view images because in AR, XR, we are always taking a video stream of your environment. And finally, because we are most of the time, a lot of scenarios are indoor, we want to be able to predict semantic planes. And with that, that's end my talk. I'm happy to take any questions. Thank you very much.
It sounds like most of the problem is solving for the 3D, the depth buffer, but then it's as simple as taking the 2D texture and mapping it directly onto the results of the text buffer, or are you doing any processing with the texture that you have as you apply it?
Yeah, so I think the question is, so if you are doing the rendering, right, in real time, you can apply the images from a camera directly onto the mesh, right? So you wouldn't see a lot of artifacts. But this is sort of a pre-process, right? So before we can create this content, we want to have some 3D models. So this is about how can we create these models offline beforehand so that we can bring in new, enabling new XR experiences. Thank you.
Great presentation. Thank you very much.
Thank you.
I wanted to ask you, have you compared your results against depth cameras? Or do you think you can improve the results if you have access to depth cameras?
Yeah, so I think to compare, I don't think we are not there yet, right? We are not as accurate as, for example, LiDAR cameras or ToF cameras yet. But I think the nice point about this is that we don't rely on them, right? They are extra hardware. If we decide to put a new camera on our smartphone, that's a very lengthy debate, right? Because we need to look at the cost and also application. So that's why we start with monocular RGB images as our input. But that being said, I believe one day maybe we will get there, right? As the second question, can we benefit from the depth cameras? The answer is yes, right? So if we have the depth camera, we can take a lot of these the ground truth data, as we call it, and we can use that to train our model. So our model, once the model sees enough data, more and more data, it will only become better. Thank you.
Great presentation. I'm curious to know, so in your final slide, you showed semantic segmentation of various objects. And in order to make this scalable, a lot more users will have their own personalized objects in their homes or other places. Is there any zero shot or single shot learning where they can add more semantic labels?
Yeah, I think that's a good direction to go. We don't right now. We are this is like a model we trained on a bunch of data, right? So the capability of the model is limited to what it sees, right? But in the future, definitely that's something we need to explore. Thank you.
What's your experience so far on how process intensive this rendering is? Can you do it in the smartphone and a headset, or do you need to do central rendering?
So these are actually not happening in real time, right? They are like the capturing the data acquisition. So once we have the model, we have the texture, I don't think it shouldn't be a problem because these are the texture mapped models. We are not doing anything fancy. For example, we are not trying to do really a complicated graphics rendering, right? Yeah.
Do you have any accommodation for windows and mirrors?
No, that's a really good question, but no. That's a limitation. Thank you for pointing that out.